Okay, got it. Okay, so I'm going to start by going back to what we've been using all semester long. And what do I mean by that? I'm talking about near-Earth gravitation. So gravitational fields near Earth, most of the time you would probably recognize. You might have a block here. And it's up in the air, some distance h above the ground. We're going to its center of mass. And we talked about there's a force on it that acts at its center. We said that force has magnitude mg. And sometimes we talked about the potential energy. We've had a few more details, but those were the two main factors. We'll call this force due to gravity, like that. All right, so what we want to do now is have a new topic. I just want to keep this here for reference. I'm just going to put a little box around it. Now we want to do universal gravitation. What do I mean by universal? Any two masses in the universe will exert gravitational forces on each other. So you can imagine a big asteroid and a small asteroid out in space, or me and you, right? Like right now, I'm attracting all of you with a gravitational force. You are each attracting each other person in this room with a gravitational force. It turns out it's very, very weak unless at least one of the objects is enormous, like the planet Earth is enormous. And so that's why we actually notice the gravitational force from the Earth on us, but not from each other, right? You don't suddenly start drifting towards your friends due to gravity. All right. In general, let's start it like this. And let's say we have object 1 and object 2. All of your notes are there, so you probably can just watch. All the same notes are already on page 117. So if you want, you can just watch up here, and then if there's something that's actually different, you can notice. All right. Typically, what we're going to do is we're going to have the center of 1 and the center of 2. Maybe I should label them differently, but we'll label them off to the side here. Here's 1. And here's 2, because we need to go from the center of object 1 to the center of object 2. In this case, that is a vector that goes from 1 to 2. And I think you agree with that. We're going from object 1 to object 2, and we're going center to center. In general, we could also make a unit vector going the same direction. Okay? A unit vector would be a hat vector. So notice the subtle difference, an arrow on top versus a hat. Pay attention to that. We know that these are related by the following relationship. To get any unit vector, you take a full vector and divide by its magnitude. Okay? So if you're wondering about this r hat. Now, strictly speaking, notice the r vector itself would have units of meters. What are the units of the hat vector? Unitless. So that's why we say this is a direction. It has no units. It's strictly specifying which way. Okay, and if you're curious, I guess, right, to be clear here, R1 to 2 is the distance, not the displacement. So to be clear here, this is the full vector that talks about how much in the I hat, how much in the J hat. This is just the distance in meters, and this is just the direction. Everybody cool with that? Now, the force that one exerts on two. Let's think about this. What direction is the force that one exerts on two? I know I'm going to be boring and accentuate that word on a lot. I apologize. I just want to stress it. I'm talking about the force on two. Which way does one exert a force on two? Towards one is probably the easiest way to say that. So that's this way. What do you notice about that direction compared to this direction? Do you agree they're opposite? Right? So the reason I'm pointing this out is we oftentimes specify the direction as negative r1 to 2 hat. That's going to be the direction of the force in general. Now, how do I get the magnitude of the force? You probably can expect the more mass you have, the more gravity you have. So that's going to be up top. We're going to have a constant, which is called big G. And then we're going to have mass 1. But it depends on the other mass too. So the bigger either mass is, the more force you get. And what do you know about gravity if you go really far away from something? What happens to the amount of gravity if you go far away from it? What do you think? If I go to a different solar system, do you think the Earth would be exerting a large gravitational force on me? No, right? Far away, it doesn't matter. So that's my point is the radius needs to go in the basement. If that didn't make sense, that's fine. That is the equation. Now, when you look at this, all chapter long, pay attention to whether something is a hat, no vector, or a vector, all right? In particular, I'm going to be clever and use this right here. If I plugged in this result, I could actually rewrite this in another way. There'd be a constant. There'd still be the two masses. But now when I plug that in, I'm getting an R1 to 2 cubed in the basement. And I get a negative vector, not a hat vector. In practice, this ends up being easier, certainly in tomorrow's lab, but in a lot of physics questions as well. This is the definition you see in a textbook. This is the one that's maybe more standard for use. Got it? They're both good. All right. Now you might be wondering about that constant. So let's do something really quick. Can you tell me the units of this constant? Does anybody see the units for this constant? Hint. Let's use this upper equation. What are the units of this? Nothing. It's an R hat. Right? R hat is unitless because the meters drop out. So let's start again. Do you agree this has no units? Okay, let's start here then. This has units of newtons. I'm going to cross multiply by that. So I'm going to get, when I cross multiply by that, what do I get up here? Meters squared. Now I'm going to divide by the two masses, kilograms squared, and the number, check out that number, 10 to the minus 11, right? You could round up and say it's about 10 to the minus 10, right? Because this is about 10-ish. That's a tiny number. Think about plugging that in. 10 to the minus 11. What if I put in our masses, like me? I'm about 100 kilograms. You, about 100 kilograms. Well, that's about 10 to the 4th. That's still going to be a tiny, 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 tiny force. Good? Gravitational forces are tiny unless one of the masses is huge. All right. What else did I want to say about that? All right. I think that's pretty good. Oh, a few points worth summarizing. All right, whatever. Let's keep going. So that's the force. Now I want to talk about energy. Oh, I know what I wanted to say. I remember. Usually we call this big G and we call this little g, just to keep them straight. Big G is 6.67 times 10 to the minus 11. Little g is your 9.8. Everybody good with that? That's what I wanted to say. If you want to talk to people, don't just call it G. Call it either big G or little g from now on. Okay? All right. In general, just a quick derivation of this. I'm not going to do the whole thing. I'll tell you more later. Potential energy change is negative work, which was minus the integral of force dot ds. Okay? And maybe I'll mention this problem so that you guys can look at it later. I'm going to give you the results of problem 13.11. I think it's beautiful. I think it's wonderful. But we have to factor in the fact that we don't have infinite time. If you want to learn more about what I'm going to say, you can do problem 13.11 at home. I'm not going to ask you to do this derivation on the test. But if it helps you understand things for you, you should do it. If you're a physics major, you should probably do it. All right? That said, most of us only care about the result of this. So I'm just going to kind of fast forward through most of this. And I'm going to cheat a little bit. I'm going to simplify my notation, where instead of having mass 1 and mass 2, I'm going to have lowercase m and uppercase m, and then just use r squared for a minute. And you could go from some initial to some final state. Now, keep in mind, you do not need to do this derivation. You need to know the answer I'm going to write in a minute. The whole point of me writing this out is, what if we took the gravitational force and stuck it in there? Okay? Well, I would need a force that's going in some radial direction, so I might do an integral along a line that's in the radial direction, so my ds becomes this. This is what I wanted to focus on, minus signs. These two are going to cancel. Do you agree? Now, I don't know if you see this or not. R hat dot R hat. What is that? What is R hat dot R hat? What's any hat vector dotted with itself? Dotted with itself. Is it 1 or is it 0? 1. It was like cross products where I hat cross I hat is 0. I hat dot I hat is 1. Now look at this. You see a G, some M's, those are constants, those are going to pop out. We get an integral of r to the negative 2. Do you agree that that's going to basically give us another minus sign when we integrate? Because you have to bring down a negative 1 when you raise the power rule, whatever. Long story short, it turns out when you do all the math on this in 1311, you discover that the potential energy is negative G M1. I'm going to stick back into subscripts now. And I hope you can kind of see that even though there's a bunch of minus signs, you get a third one from doing the integral, and that's where this one came from. And so I'm going to put in another minus sign here in red here, just to make sure it's really obvious. I hope it makes sense that this is r to the first power, right? The force has an r squared in it. Notice the energy, right? If you think about it, You got newtons times meters, right? So that's going to get rid of one of the meters in the basements. Joules are newtons times meters. At first glance, most students feel very uncomfortable with this for two reasons. Number one, we're not used to thinking about negative energy. It's okay though. Remember, we can think about energy as being like money in the bank. And we all agree you can have negative money in the bank. You can owe somebody money, right? That's effectively what this is. Number two, most people think this equation looks a lot different than this one, doesn't it? It turns out, if you do the right Taylor series on this equation, you get back that term. That is problem 3.12. So if you want to see I think it's 13.12, right? This is another question, not on the test. If you are a physics major, you should do it. Okay? So if you're curious how you get from this to that, we can talk about it later, but I'm more focused in making sure you can pass this class. Sound good? All right. It's really interesting to me. Enough said. I want to talk about it. I got to stop myself. Okay. I want to talk about an example really quick, which I think will make sense of this minus sign for you. And I remember thinking to myself, it was very confusing at first. So let me see if I can do an example here. And maybe I'll emphasize that in red. Is this minus sign a problem? Okay. Let me give you a before and an after picture. All right. So let's say we have blue one here and a green one right here. That's the initial state. Let's say one doesn't move and two goes way over here. All right. Over here, I might say R12 initial. Notice I sometimes leave out the word two. In this case, the distance between them is small, and in this case, the distance between them is big. To be clear, that is R12 initial, and that is R12 final. Everybody okay with that? Let's think about what happens to these numbers. U initial, it's going to be negative because of the minus sign. Everything else, G is a positive constant. This is a distance. It's a positive value. Mass is positive. So it's going to be negative. Is it going to be negative and big or negative and small? According to that equation, relatively speaking. We're 1 over small, so that's going to be big, right? If you go 1 over 0.1, you get 10. So negative and big. Okay? Versus here, U final would equal, it's still negative, but you agree it's negative and small? right? Here's what matters in real physics problems. We don't care about any one energy state. The only thing that ends up mattering in any of our equations is delta U changes for this state. Is delta U positive or negative? That's right. Let's put in some pretend numbers. Let's say this was negative 100 and this is negative 10. I'm just making up numbers, and obviously there would be joules, right? It might look something like this. Notice if you punched in the numbers, it's positive 90 joules. You increased, it's positive. This is all that matters. If you raise the mass up, potential energy increases as we expect. So even though it's negative, because the radius is in the basement, it behaves just like before. As you go up, your energy increases. Now it gets a little awkward to say it increases because people are like, well, negative 100, 100's a bigger number than 10, awkward. So what I like to say is this is a more positive or less negative. Rather than say go up in energy, I use the words it's less negative or it's more positive. So I will use those words when I'm talking. Does that make sense? It's the same thing as going up, but I think it describes the situation a little better. What else did I want to say about that? Oh, last bit. Which one of these masses has the energy? 1 or 2? Let's assume for some reason this one is a 1 kilogram and this one is a 2 kilogram, right? Whatever it is, and the distances are such that these numbers work out. Which one has the energy? Is it 1 or 2? Why do you say 2?
The one that's moving?
No. Yeah. Good guess, though. And here's the deal. When we were talking about this on the planet Earth, the Earth doesn't move. So I say, I lift this up in the air. The napkin or whatever the eraser has the potential energy, right? Strictly speaking, we don't want to think like that. Let me ask you this. Let's say I was holding them here, and then I spread them out, and we're in deep space somehow, and then I let go of them. Wouldn't they both start coming together? Now, we do expect that one would move twice as fast because it's half the mass, but they would both move. So I want you to think of it not as one object having the energy, but they share it. And in particular, they share it in the gravitational field between them. But okay, if you don't want to think about that, just think of that as shared energy. If I brought in another mass, all 3 of them would share it. If I bring in 16 masses, all 16 of them would share it. Got it? So it's shared amongst any masses that are there. All right. See if there's anything else I want to say. Let's go back to the bottom, just before 13.1 on page 117. A few key points worth summarizing. Potential energy is associated with each pair of masses. It's not in one mass. They share it with their gravitational fields. Notice potential energy, these are scalars, just like chapter 8, scalars, no vectors. Potential energy is always negative. What's the biggest radius you could think of? Give me a big number. Starts with in. Infinity. What happens if you put infinity down here? What do you get for you? 0. So only when these masses are infinitely far away is there 0 potential energy. So if you go to a different solar system, you're basically an infinite distance from the planet Earth, approximately. Right? Depending on the problem, it's not necessarily true, but yeah. If you go really far away, we say you have escaped the planet. Right? And so then your potential energy is 0. It no longer has an effect on you. As you move farther away, You're not seeing any changes in U. What if you go from like 10 billion to 10 billion plus 1 meters? Basically, you got 0 either way. There's no change in gravitation. That's the same thing as saying the object had no effect on you. Right? You're really far away, changes in U go to 0. Lastly, gotta watch this. We always watch the minus sign, and notice this is not squared. The force is squared. The energy is to the first power of the base. Got it? These are on your equation sheet, but I see it every year. Someone accidentally writes a squared in the energy or forgets the squared in the force. So watch out for that. Okay, and then maybe summarizing over here. I think I said this, but I'd rather double check. I just want to point out, in all of these problems, we're talking center to center distance. Center to center distance. Okay. Any questions on any of this? Okay, start reading 13.1 while I erase the board. 13.1. This is one of the few times I'm going to go pretty slow. So if you're bored and you need to grab a laptop, we can get that done. Okay. If you don't want to listen to me, I'm not offended. You guys know when the next total solar eclipse is? It's April 8th, 2024. Goes through Texas up to Schenectady, New York, and Mazatlan. So if you guys are in Mazatlan, let's party. I'll teach online that day. We'll see if this video is being used on that date. Anyways, yeah, check it out. All right. April 2024. What was I doing? Oh, shoot. All right. Here's the sun. Here's the moon. Here's the Earth. Okay, somehow they're perfectly lined up. Great. At one instant in time, cool. Now, did I hear Vince back there?
Yeah.
When's the next solar eclipse?
2024, right?
What date?
April? Is it April 8th?
See, I told you. I just told him I'm doing a solar eclipse problem. Thanks, Vince. Yeah.
No problem.
Right on.
Are we going to Texas?
Yeah, we're either going to Texas or Mazatlan, as long as the students pay. All right, see you, man. All right. Now, to be clear, this is, sorry, let's get back into this problem. So we got the sun and the Earth. There's going to be a distance between them. There's going to be a distance between the Earth and the moon. Okay. And just to be clear, as far as distance goes, do you agree Earth-Sun is the same as Sun-Earth in terms of distance? Not the vectors, but just the distance. So on this problem, I'm only going to use the distance. It could be a little bit sloppy. So remember, the distances are equal, but the vectors are opposite. And by that, I should maybe make that clear. That's going to matter tomorrow in your codes. If you're using a vector, it's important that you get the order of the subscripts right. If you're just using the distance, you don't have to be so picky. Maybe I'll put this down here too. Going from the moon to the Earth is opposite of going from the Earth to the moon. All right, and then I got a bunch of constants here. I got to write all these down. I know it seems boring, but I think it's important that we have the numbers to look at. So I'm going to take a few minutes to write some numbers. Sorry. 30. If you're wondering how they get these, we could explain that later. Like, you don't stick the sun on a balance, right? How do you get the mass of the sun? More on that later. How do you get the mass of the earth, right? Talk about that. But for now, let's say somehow people figured this out. By the way, that guy Vince right there, he knows a lot more about astronomy than I do. If you have any extra questions, we could bring him in as a ringer. Oh my goodness. Finally, I think we got some different numbers here. Radius Earth Sun is the Earth Sun distance. 1.5. All right, almost there. One more. Okay. It's important on your final exam day to be quick at using these numbers in your calculator. So we're going to do a bunch of really simple calculations just to make sure you're lightning fast with the calculator. So you might take a second to get that out and try and get used to your scientific calculator, because that's what you need. If you need a couple, does anybody need one? You do, I've got it here. Okay, I got 3, 4, whatever. In particular, when we're doing astronomy problems, you got to get fast at using the EE button or the E or the times 10 to the button or whatever you want to call it. So that's kind of our goal here. Maybe before we start punching in numbers, let's look at the following. This is not to scale. I know you're shocked that the Earth and Moon aren't an inch away from each other and the sun just 3 inches. But in this case, let's take a second to look at these numbers. This distance here is 10 to the 11th meters. Now look at the radius of the Earth. 10 to the 6th meters. That's about 100,000 times smaller. So do you agree, if this was drawn to scale, the Earth would be a dot smaller than that dot? Why am I bringing this up? Even though we think the Earth is huge, on this scale, it's a point mass. You know what I'm saying? On this large of an astronomical scale, we could actually treat the Earth like a point mass. Check out the sun. The radius of the sun is 10 to the 8th meters. If I was going to draw that to scale, it probably would be about the size of that dot. That is approximately to scale, right? 1,000 times smaller, maybe even a little smaller than that. 10 times smaller. Point being, the sun, even though the sun is 10 to the 8th meters, that's still 1,000 times smaller than this, approximately. So it's okay to treat this, and obviously the moon is small too. It's okay to treat these all as point masses. Is everyone okay with that? When the distances are huge, you could treat them as point masses. All right. Okay, let's do part A now, finally. Let's get the force, gravitational force exerted by the sun on the Earth. So I want the force of the sun on Earth. And notice, I'm just going to get the magnitude of it right now. Let's get the magnitude of it. So to be clear, I'm going to emphasize that I'm just getting the magnitude. I have not drawn the arrow on top. That means I can leave off the direction. It's going to be G, mass Earth, mass Sun, over radius Earth, Sun to what power? 1 or 2? For the force. 2. Okay, punch it in. Let's just check it. I know you gotta get fast at this sometime. It might as well be right now. 6.67 EE negative 11 times mass of the Earth. 5.96 EE, or times 10 to the 24 times 1.99 EE 30 divided by, I'm going to put parens around it before I square it so I don't screw it up or have to think. RES is 1.50 EE 11 end parenthesis x squared, and I got 3.52 times 10 to the 22. What are the units of force? Newtons. So take this time to get fast with your calculator. All right, make sure you can handle the EE button or the 10 to the button. Is there anybody that needed a practice calculator? It looks like you're all got it. Okay, good. So that was part A. Try part B. Do it again. You want to be lightning fast with this. This is not what you want to be limiting with. I'm testing. Force of the moon on the Earth. What's that? Oh, question?
You press double E on the color.
Yeah, I use the EE. Watch this. So like I use 6.67 EE negative 11.
All right.
Got it? And so that's a fast way to do it. You could also use the, I think, 6.67 times 10 to the negative 11, but I don't like that one. It just, yeah, it's the same.
All right.
Cool. Yeah, and if anybody else needs to see that, I'll walk around and show them real quick. It's just, if you get faster at this, you can type in your prefixes with the EE button, and then you don't have to do all the conversions. You can just do them on the, make the calculator do it for you. It's a way to be fast. Which one do you think is going to be bigger? The force that the sun exerts on the moon, or the force, the sun on the Earth, or the moon on the Earth? Which one do you think? Let's find out. Let's punch it in. Earth, moon is right there. .36 times 10 to the 27. All right. Let me see if I forgot the square. Let me do that again. 6.67 EE negative 11 times mass of the Earth, which is 5.96 EE 24 times mass of the moon. What was mass of the moon? Oh, I punched in the wrong number. That's wrong. I was wrong. Okay, I didn't use the right mass. 7.35 EE 22 divided by 3.84 EE 8 x squared. All right, 1.982 times 10 to the 20. Does that sound better? All right, sorry about that. I punched in the wrong mass. All right. Now, you guys happen to know anything about the tides? In particular, which do you think has a larger effect on the tides? The sun or the moon? In your experience? The moon. And yet, which force is bigger? The sun. Now, I hope you could indulge me for a second. Do you agree that both of these equations scale as 1 over r squared? Meaning the functions of these forces look like 1 over r squared? I'm going to draw that. This is 1 over r squared, and here's r. When you're at very small values of r, what is true about 1 over r squared? Is it big or small? What's that? If r is close to 0, what is 1 over r squared? Close to.
You mean like a big number? Like
Really big, right? So we expect it to be really big. When r is really big, what happens to 1 over r squared? It's small. Now here's the deal. Notice RES is a really big number. So we're way out here. There's less change in the sun's gravitational force from one side of the Earth to the other. The moon, with its much smaller radius, is closer to this part of the curve. And so the change in the moon's gravitational force on the Earth is more significant from one side of the Earth to the other. Let me say it again. There's a larger change in the moon's gravitational force if you go from here to the opposite side of the planet than if you do that with the sun's gravitational force from here to the other side of the planet. The sun is basically the same force on either side of the planet. The moon, there's a small change. That's it. Got it? And that's why there's a more significant effect. If you are passionate about learning about the tides, you could obviously YouTube it, but you could also look at page 125. It turns out it's a complicated thing. And it's not on the text. Got it? Page 125, if you want to learn more about that, you could do that on your own, but I recommend watching some cool videos on the internet instead of doing this problem. Cool? So if you're passionate about understanding tides, that gives you some information on that. Oh, look at this, a fun resource at the very bottom of that, NOAA Tides Education. So right here after those bullet points, just underline that. If you want a web search, I did a bunch of web searching and that's what I thought was the best. It was easy, it was informative and fun. All right, so NOAA Tides Education. Okay, and that's a pretty damn reliable source right there. Enough said. We've done A and B. Good? How are you feeling on the calculator? Getting there? Getting used to the EE button?
Yeah.
Okay, it's kind of nice, right? We talked about it on week 1, if you believe it. But okay, C. I want the potential energy. What letter do we use for potential energy? U, and what did I say? Earth, sun? Earth, sun. I want U, Earth, sun. That equation was, does anybody remember the equation? Negative, 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 negative G mass Earth, mass sun over what was it? What is it? RES, not RES squared. Excellent. Maybe I should do that in green so it matches, huh? Whatever, it's too late. So the trick is you got to remember, now notice in this case, couldn't we just take this number, multiply by RES and flip the sign? Do you agree we can do that? Do it. Punch it in real quick. What was that number? What was it? I think it was that one. Times, what was radius Earth Sun? 1.5? EE 11. 5.27 to the 33. Negative. What are the units for energy? The real gem of a unit? Joules. It's not going to get any better. We got to get through this dumb problem. Let's do D. I want Earth, Moon. I know it's cheesy, but let's do it. We got a negative. Sometimes a little repetition will lock this in, right? You want to be fast. You do not want to be learning the calculator on exam day. That should be this number times that number with a minus sign. That should be this number times that number, 84. And then we got to remember the negative 7.61. We got the power 10 to the 28. All right. Got it? So I've got the potential energy from the Earth and the Sun and the potential energy from the Earth and the Moon. So if I want to get the total potential energy, I just add these up and I got it, right? Are you feeling good on that? I'm going to say that again. Listen carefully. We got the Earth-Sun potential energy. I've got the Earth-Moon potential energy. We got it. I'm just going to add those up and get the total potential energy. You like that? Or let me rephrase. That's completely wrong. Why is it wrong? Yeah, all right. I'm glad we covered this. How many objects do we have in our picture? 3. How many pairs can you make out of 3 objects? How many pairs? 1, 2, 3. The 3 share the energy. You need all 3 pairs. Got it? So it turns out, I just want to focus on this. The total potential energy is equal to UES plus UEM, but we can't forget the third body, the third pair, excuse me. The last one would be what? Moon, sun. Now, to be fair, this one might be a lot smaller, and so this might approximately be the total energy, but it's not exactly the total energy. The total energy is you need to add up all the different pairs. Got that? So I was trying to put you to sleep and it worked. All right, watch out for that. Potential energy, you get the total by getting all pairs. All pairs. All right. All right. All right, that's that problem. Feeling good on it? We basically did the other parts and talked about it. I didn't punch in the numbers for this, but do you agree you could punch in some numbers and get it? At this point, I think we're good on that. Go to the next page, 118. I'm going to keep cruising. I got to erase the board. Erase. Well, you read the next one, 13.2. Keep erasing. Still erasing on Zoom. Still erasing. best I can. All right. 13.2. Okay, so now I want to talk about some practical aspects. Let's say we have a planet with some radius r, maybe it's the Earth. Well, it's 6370 kilometers, is that right? Mass. .96 times 10 to the 24. What's that? 97. Did I get the other one right? Yeah. Okay, thanks. How about that? In practical terms, we're going to do a very simple model here. We're going to assume the Earth is a perfect sphere, perfectly flat, no mountains on the surface. At first glance, you might say that's absurd. Does anybody happen to know how big this radius is in miles by chance? 4,000-ish. It's approximately 4,000 miles. Now think about this. What's the tallest mountain on Earth, approximately? In miles? Less than 10. What's the deepest trench? Mariana's Trench or whatever, right? From grade school. How deep is that? Couple miles, less than 10. Now think about this. The deepest spot on Earth to the point farthest from the equator, which is actually in what, Ecuador or Peru, it's slightly, whatever, I don't want to go into that. But basically from the tallest mountain to the deepest trench is maybe 20 miles. Do you agree 20 miles out of this is negligible? There's that old story. Have you heard this about like an orange peel or a ping pong ball? Right? And most people think the Earth, if they went out from space, would be as rough as the surface of an orange, but it's more like as smooth as a ping pong ball from space. So yeah, basically the Earth, we're going to assume it's super smooth and there's no mountains. And at first you're like, man, that's crazy, dude. But it turns out it's actually a pretty good approximation. The actual variation from the highest point to the lowest point is less than 1%. Okay? It's a fraction of 1%. Whatever. All right. I didn't even have that much caffeine. I don't know what's going on. Let's say you're sitting here at some altitude, h. So h will be called the altitude. Normally, we talk about the altitude h above a planet's surface. For example, when you talk about a plane flying, they don't talk about the center-to-center distance between themselves and the Earth, right? Planes always talk about we're 30,000 feet in the air or so many thousand meters in the air. Just to be clear, that's an H, not an N. Sorry, that's so crappy. Well, in this case, notice the radius here. Sometimes you'll see me say little r is equal to r plus h. Okay? Where h is the altitude. So in a practical problem, how would this change things? The force due to gravity from big G would be G, mass of whatever's sitting up here. Let's say there's some object up here with some mass, little m. Instead of using r, we oftentimes will use r plus h. Okay? Is that looking good or not? I forgot the squared. Good job. You caught it. All right. So far, so good? Now, I want to point something out. Near Earth, and I'll say near Earth's surface, We need that to be true. So notice these two equations match up if we make the following identification. And maybe I'll put this mass here in blue. Notice everything up here that's not this m is basically little g as a function of altitude. Cool? Oh, I guess that's supposed to be radius of the Earth, but whatever. I'll just erase it right there. Okay, now, when we get into this, let's plug in some numbers here real quick. What if we set the altitude to 0? What if we set the symbol h to 0? Then it would be g me over radius Earth squared. Punch that in real quick. (6.67) E negative 11 times, what was it, 5.97? Is that right? EE 24 divided by the radius of the Earth, which was, now check this out. I want to show you how to use this one with the EE button. I'm going to type parentheses so I don't screw up the squared, 6370 EE3, because this kilo is a 3. So 6370 EE3 is how you type that in. And then you square that. You recognize that number? Let's check the units. G is newtons times, what was it? Meters squared over kilograms squared. Mass is 1 of the kilograms here, is that right? And then here, what do we get here? Meters squared. So now, that drops out. This drops out one of them. But a newton is like an mg. So a newton is a kilogram times a meter per second squared divided by a kilogram. Okay, so far so good? What happens to G as you go up into outer space? What happens to little g, I should be careful, as you go into outer space? What happens to the altitude as you go into outer space? It gets higher, so what happens to the denominator? So what happens to the value of G? Smaller. I punched in some numbers in question 13.3 and a half towards the bottom of the page. For example, I found out if H is equal to 400 kilometers, G is, what was it? 8.7. If that helps you get a feeling for that. Now think about that. 400 kilometers is pretty far up there, right? You can go 400 kilometers into space. That's where we put some satellites. I mean, that's a crazy amount of distance. And you still have almost the same factor for G. Almost. Right? All right. What else did I want to say about this? Oh. You guys know what value G is from your homework usually? What have we been using all semester? For G, little g. 9.8. Some people use 9.81. Maybe you've heard the worldwide average is 9.806. Turns out in Santa Maria, it's about 9.79, or maybe just under 9.8. Every place on Earth is actually a little bit different. So remember, we made some assumptions here, right? We completely ignored highs and lows. Those things matter in the third sig fig of G. So why keep it to there? That's why all semester I've only been rounding to 9.8, depending how much uranium is near you. If you're near a mountain that's near a large uranium mine, that might slightly skew G, right? Or a large uranium deposit, excuse me. Yeah, and obviously as you go up or down on a mountain, that might change the value of G. Is it enough for any of us to notice? No. But if you were doing very sensitive equipment, you actually need to look this value up in a table and get the local value of G. Cool? Anyways, I thought I'd just mention that because we kind of gloss over that at the beginning of the semester. All right. Now, I don't usually try and force you to do a plotting question. I believe this question, 13.2, asks you to plot this. Please do it. The reason why, when I was writing this chapter in the book, I discovered I got a lot better by plotting it. So what happens when you plot is you have to force yourself to be better at dealing with units. So it's not going to take you that long. It'll take 5 minutes. Try to actually do it. And you have to force yourself to fight through these different units. All right. So that's basically it. And notice we did F. You're supposed to also make a plot of U in this question. So you can make sure you get the units right, the squareds right. So do that at home, make a plot, see if it works. It says it forces you to deal with prefixes and scientific notation properly. Okay, that's enough said. You want to do one more or you want to take the break? Will you call? Who wants the break? Oh, you guys are hard chargers. You guys are crazy. Okay, let's do 13.3, an orbit problem, and then we'll take our break. All right, that's actually a good spot. We got an empty board. That's cool. Let's do it. 13.3. Okay. This is one of the two styles of questions I might put on an exam, so maybe put a star next to this one for the final. You should basically know how to do this problem with different numbers or different parameters in it. It's also kind of interesting too. Cool. Finally, we're going to do something moving here. Okay, so we have some orbit. The altitude is h. We're going to try and learn about energy and forces, I believe. We're going to have a CubeSat. I don't know if you guys know what a CubeSat is. Has anyone ever heard of a CubeSat? If you're into this, if you're transferring to Cal Poly and Stanford scientists, I guess, came up with this idea. They're basically small 1 kilogram satellites, and you can launch a bunch of them at once. And it turns out if you're going to Cal Poly, they have a lab there where students can actually work in the lab and be the space control center for these little CubeSats flying around this planet that we live in, I guess. Anyways, whatever. You can learn about that later. CubeSats are a real thing. Look it up on Google or something. Okay. We're going to say this planet has mass M. I'm going to put a little light shading in there just so I can tell that's the planet. Not an orbit or something. Zoom height. Okay, so there's my planet. There's my CubeSat going around there. That has mass little m. Right? So a lot of times, instead of writing subscripts, what we're going to do is we're going to use one of the masses as capital M, and the other mass is a lowercase m, just so we can keep straight. Okay, part A. Oh, and one last bit. We're going to say that M is much, much greater than little m. Effectively, can imagine big M as being at rest. Think about this. Why is that okay? By Newton's third law, these are going to exert the same force magnitude. If this mass is huge, it ain't going to move much compared to that one. Got it? Okay. Now we're finally ready. Gravitational potential energy. Somebody tell me the formula for gravitational potential energy for this one. Not MGH anymore. What is it? Negative. That's the first word I wanted to hear. You got G, M over somebody else. Is it R or R squared for potential energy? R, you got it. Now in this case, we need to use the altitude, just like before. And that's the formula. Just keep that in mind. That's our reference energy. Okay, we're going to keep that in mind. As the altitude goes up, the energy goes more positive or less negative or closer to zero. B. One's a little more subtle, I think. Ooh, I want the speed of the satellite in terms of these other parameters. So for right now, let's assume V is an unknown. How would you figure out that V? Looks like an object going with constant speed in a circle. What's that? Maybe you could, but I wouldn't start there. That's a good guess. What's another tool we use this semester? Circular motion. Angular momentum is a good idea. That's not it either, but that's very related. Chapter 6. Not energy. That's also good, but what's the other major topic that we covered this semester? Not energy, not kinematics, not angular momentum or momentum, but rhymes with horse. Yeah, force. This thing's going in a circle at constant speed. What's the acceleration? Nope, I got you. We're going in a circle at constant speed, so it's AC. You know what I'm saying? Doesn't AC equal V squared over R? That's how we get the speed involved. Okay, what's one force acting on this satellite as it orbits? What is it? Not mg anymore, but mg only works if you're near the Earth's surface. So what's the new way of saying mg? Big G, MMR, whatever, yeah. So, okay, so there's going to be a big G. Let's get a free body diagram here, right? There's a force due to big G now instead of mg. So that's the trick in this chapter. Instead of writing mg, now we start writing force big G, which was G M over R squared. And I'm just going to do the magnitude because I've shown the direction with an arrow. What's the other force? What force is keeping it up in the sky? You guys can't see me smiling. What's that? Gravity. Gravity's causing it to fall down, right? There is no other force. I was trying to trick you. That's why, yeah, this mask is great. It hides my smirk. It's good. All right, so in this case, you might say, what about air resistance? You're in outer space. Hopefully that's negligible. You guys remember that a few years ago? That's not completely negligible. Remember that weird space station that was going to hit the ocean and when Taco Bell was going to give away 1 million tacos? Do you remember this? No one remembers this? This is like the stuff I focus on. Taco Bell said if the space station hit this one area, they put out a target in the Indian Ocean. They said if it hits it, everybody gets free tacos. You think I'm making this up? I don't know. Look it up. I swear it's for real. Anyways, there's no other force. One of the common misconceptions is we need some other force to keep it up there. More on that after this problem. I promise to come back to that. For now, there's only one force. Gravity forces it to go in a circle. Right? We need a force towards the center. We got it. We don't need other forces. So after all this is equal to Wait, which mass? I know I need an MA here. Which mass am I drawing here? Little m or big M? This is the cube set. That's little m. That's why I use little m here. The mass that you use in the FBD, here, little m, is the mass that you should use on this side of the equation. Cool? Right? So that is going to cancel out. And I get notice it's kind of handy to leave it in terms of little r, and then only at the last step do we plug in big R plus h. So let me see what I get for V. Square root of G M over little r. Is that right? One of these cancels one of those, we get a square root, and now I'll write this in terms of the variables requested in the problem. That's the speed. Cool. C. Kinetic energy. Okay. I want the kinetic energy here. What formula would you guys use for the kinetic energy? What formula would you use for it? One half, I agree. What else? Inertia times. That would work. What is the moment? Now, do you agree we could treat this basically as a point mass? Remember that, all that mumbo jumbo? What's the moment of inertia for a point mass? M, in this case, it would be R squared. But what's R squared omega squared equal to? What's R omega? Nope, nope, that's R alpha. R omega is then V tan. You could use either this or that. I did not explain this when we were in chapter 8. But it turns out if you have a point mass that's going around in a circle, you can use either this kinetic energy, where it's the I omega squared, or you could use normal translational. Think about it. A point mass orbiting with speed omega is the same as a point mass traveling with speed v in terms of its kinetic energy. Did that make any sense at all? You could use this or this, just not both. Okay, because it's not spinning and going, it's just going. All right. You can either view it as this type of a spin or this type of a translational v. Now, I don't know about you, in this case, since we just solved for v, I think I'm going to go with the last version, just because we just already used it. So here, for this problem, I recommend well, now I got the square gets rid of the square root. Does that look familiar at all? Does that look like anything else on the whiteboard? A little bit? It looks a lot like this one, except for what? This is negative, yeah, and the half. Okay. So notice, I'll just point this out. This is equal to negative 1/2 of the potential energy. So far, so good? It's negative 1/2 of that. The negative gets rid of the negative, and the half gives me the half. Part D. What about the total energy? Let's call that E total. In this case, to be clear, the satellite doesn't have all of the energy, but the satellite is the only thing that we're seeing move. So oftentimes we say the satellite has the potential energy, but in reality, it's shared. But what's the total energy of this system? The kinetic plus the potential that's shared, and we get what? Shouldn't it just be half of that? Right? Basically, this cancels out half of that one, and it stays negative. So we get negative, we get a 1/2, we get a GMM all over R plus H. I know this was a lot of work to get to here, and you get to your break. I don't know why why didn't I tell you to take a break? Sorry. The last half of class will be quick. That's all I can tell you. We're almost there. Here's what's cool about this. What's the total energy? Positive or negative? Positive, 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 positive. The answer is negative. This goes back to what I was saying before. As you go to higher and higher orbits, you get less and less energy. You're less and less trapped by the planet. The negative energy is a sign that you're trapped in an orbit. Is anybody in here into chemistry? Everybody's scared to say that. Well, maybe you remember in chemistry minus 13.606 eV for the energy of the hydrogen atom. Remember it was negative? That's because in a hydrogen atom, the electron is trapped by the nucleus. And so negative energy just means you're trapped inside an atom. It takes positive energy for the electron to break free. You have to give the electron energy to break it away. Similarly, we need positive energy. I would have to give some energy to this satellite to help it break free of the planet. That's what the negative energy means. You're trapped in an orbit. Okay. All right. If we go to a higher orbit, what happens to E total? What would be a good way to describe that? If we go to a higher orbit, that's the same thing as saying the altitude increases. What happens to the total energy? What would you say? What's that? I would like that. Oh, I caught it. What would be the other way? Less negative. So we don't say it increases. I would say it becomes more positive or less negative, whichever way you want to say that, just because that makes sense in all scenarios. Good job. Nice. Period. I want the period of this orbit. Does anybody know anything about period? What was the symbol we used for period a few weeks ago? T. And I used that weird double stripe T. That was the period. What does it mean? Period means what? Time for one revolution. Now in this case, I'm going to call it a revolution and orbit. Am I still on, Alan?
Yeah.
Just barely? Okay. So the period is the time to get around once. What does that relate to on the board that I've already written? Anybody? The period, which is, how can we get the period involved in one of these equations? I see a bunch of junk here. Which one instantly relates to the period? You remember? Let's do a quick unit analysis. This is joules. What is this one? Meters per second. Joules, joules. What is period? What are the units of period? Seconds. Huh. Which one of these might relate? Hey, if I could just get the meters for one orbit and divide by the seconds, I got me some meters per second. Well, what's the meters for this? What's that? 2 pi is the angle, that's not the meters. 2 pi is how many radians. How do you get how many meters you travel? Who was the roundest knight at King Arthur's table? Circumference. My gosh, that's good. Okay, just remember this. If I write it, you probably remember it now. Remember we talked about that earlier? Distance for one orbit divided by time for one orbit equals the speed. Remember when we were swinging the cup of water on a tray? Was that you that did the water cup? No, who was it? Oh, whoops, my bad. My bad for being too brutal. Okay, let's just solve this real quick. What is that? 2 pi r over v? It seems like something I would screw up, so I'm going to double check. Meters divided by meters per second. The meters cancel the second. Okay, we're good. Now I'm going to go back to this version, right? So the trick when you're doing this is try and use little r until you get to the last step. In this case, maybe I'll even just leave it at little r. Ooh, got a nasty fraction here. Well, in this case, I could simplify that. Sorry, I'm so low on the board there. Can you still see it all? I'll rewrite it up top. I'm going to get 2 pi over the square root of gm, mass of the planet, times, what is it? R to the, what do I get? R to the what power? I've got an R up top, and then I got a square root of that. What do you get? Yeah, 2 halves, and then this one flips up plus another half. That's going to be 3 halves. How do you weigh a planet? You watch it, and you see how long it takes to go around an object. And you could figure out its radius, or yeah, you could use the distances to get the radii. Basically, this is what helps us weigh planets. If we could time their orbits, we could try and solve for their mass. You could find some object that's orbiting the planet, figure out its radius and its time from watching it in the sky, and that's how you mass a planet. Trippy, eh? So for example, the thing that's important to see here, the mass of the large object is what shows up. So if we observe a satellite like the moon, and we know how long it takes the moon to go around the planet, and if we could somehow figure out the distance to the moon, we could get the mass of this. So maybe you heard about them putting a bunch of, well, let's show you. This is a retro reflector. Whoa. What's shaking in here? Oh, right? Here's a big one. Here's a small one. Just a reflector. The cool thing about this is no matter how you shine in a beam, it's going to bounce off all three and go straight back. You can put a laser on Earth, put one of these on the moon. You can time how long it takes the light to travel, and that would get you the distance. And you can actually figure out the mass of the Earth to a number of sig figs. Pretty cool, right? Or yeah, that's enough on that. Kepler's third law is pretty cool. Enough said. There's a bunch of numbers there. You can plug in the numbers at home. You can do part G at home to make sure you can plug in the numbers, okay? Now there's the CubeSat. Enough said on that. I said I would come back to what keeps the thing up there. I'm going to do that really quick. That's fast and does no math. And then you get your break. Sorry it's so long tonight. Oh, this seems a little crazy. Just take a second to imagine this. You guys can veg out. Okay, watch this. Let's say you have a planet And let's say on top of the planet is a tall mountain with a baseball player. Okay? I want you to think of it like this. Let's say the baseball player throws the baseball really weakly. You guys just going to fall down. What if they give a little more heat to it? Going to fall down even more. Well, what's happening here is, as you throw it faster and faster, it covers more of the curvature before it hits the Earth's surface, right? Well, what if you throw it super hella fast at just the right speed? It's going to keep falling. 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 Whoops, I looked away. It's going to keep falling. And it's going to hit you in the back of the head. The idea here is, whoops, that's so sloppy. If you throw something fast enough and there's no atmosphere and no drag, the object will keep falling forever. That's what's happening in the satellite. Nothing keeps it up there. It's constantly falling towards the planet. It just never hits. There, let's get it right. Woo. Woo. That was too long. Sorry about that. 5:59. All right, oops. All right. Let me see, you can see this just a little better. All right. So I have a simulation here. Oh, time to get back to it, right? So let's take a look. Just for fun, I have a simulation. Now, in this case, we see we have an orange mass and a light blue mass, and there's a force exerted on the light blue mass. But if it helps, just in case there's colorblind stuff going on, we'll call this one object one. This is object one. Oops, that's terrible. This is object one. And we're looking at the force on two. So that's this one. This is object two. Now, at first, and notice we've got the gravitational potential energy. So down here at the bottom of the screen, you can see the gravitational potential energy. Notice it's negative. I didn't care about sig figs. And we got the magnitude of the force and the force vector. So I thought I might show you what this looks like in the code here. Let's clear all that. Let's go look in here. And I'm going to make this bigger. This is what you're doing tomorrow in lab. This is boring, just drawing some coordinate systems. We've got big G, the universal gravitation constant. Now notice there's this new concept, what I'm going to call a scale factor. Those of you that have done quite a bit of coding know what that's for. Basically, what we're going to do is we don't want to calculate any forces incorrectly, but sometimes the forces are either going to be really big or really small, and we need to scale them. So more on the scale factor in a minute. That's used to scale the arrows to change how easy it is to see things. I created two different rocks. I gave them some positions, and I created some new attributes called their masses. If we go down into here, the 1 to 2 vector, this is probably the hardest part for students because everybody flips it. Remember, we've got object 1 here. We've got object, let me do it in a darker blue just so it shows up. We've got object 2 here, right? And I want to go from 1 to 2. So I want to go from 1 to 2, center to center. That's R, 1 to 2. Okay. Now, when I do this, notice this is like the final position, and this is like the initial position. So that's why it's final minus initial. If you can get that down, hopefully tomorrow's code will go well. Remember, this is going to be live streamed, so if you forget any of this crap, you can try and remember this is approximately 1 hour and 40 minutes into class in the live stream, or whatever. 1 hour and 40-minute mark in the live stream. Now look at this force. So I'm looking right here. The force of 1 on 2, I've got big G. I've got rock 1 mass. That's the big one. That's the big yellow one. And then I got the smaller blue one right there. Now I do, look what I did here in the code right here. I use the R vector over the magnitude cube. So if I could clear that last line, I'm basically read this sentence here. In the code, it's easier to use R vector over R cubed instead of R hat over R squared. That said, you could actually do the same exact code this way. This would give me the same force. I could go this dot hat, that would take the hat vector, and then I could use the magnitude squared. Those two lines of code, 27 and 28, would give me the same thing. Or maybe you could say negative hat of this vector if you prefer that style. So those would all be correct ways to get this. You could also write it like this. You could say, whatever, that's good enough. Okay. So now let's go up here and look. I've got one of them at 0 and one of them at 6. And let's run this thing again and look at it. Okay. So the force is about 7.5 newtons, 7.4. Got that? I'm going to write that down here. 7.4 newtons when the distance was what? 6? And I'm assuming that was in units of meters, okay? So now let's go into the code and let's, oh, and notice, let me write one other thing. So that was the force. And then the potential energy was negative 44. Ooh, 44.4 almost. I like that. Okay, joules. Let's just say it like that. So let's go into the code. What's going to happen if I double this to 12? What's going to happen to those numbers up there? So I'm going to run it again. We got R was 6. I got those set of numbers. What do you think? Take a second, discuss with your neighbor. What should happen to the values of F and U when I double the distance? Or think to yourself if you're just flying solo back there, all right? In particular, by what factor, what numerical factor will each thing change? I doubled the distance. Will the force double? Will it cut in half? Will it do something else? What about the potential energy? Will it double? Will it cut in half? I'll give you 10 more seconds. Here we go. Double the distance. Is that what you expected? So now we've got R equals 12 meters. Can you tell the factor that changed in the force? I'll call this R prime. So this will be force prime equals the original force divided by what? Can you tell? About? It used to be about 8. Now it's about 2. 4, because it's squared, right? If you double it, then square it, you cut it by half. Or you cut it by a factor of 4. So it's the old force divided by 4. What about the potential energy? U prime is exactly half. Do you agree? So that's something that's a little bit tricky when you're doubling the distance. The energy cuts in half, but the force gets cut in a factor of 4. And you're just punching it in to get the ratio to show it's 1/4. Did you get it?
Yeah.
Right? Okay, so good. She actually checked it. That's awesome. Now, let's try another one. Any questions on this? What's cool about this is, I know this may seem a little bit silly, but now we can do weird crap. We can stick it in the z-axis, right? Right? We could have one of these off axis and stuff like this, or give me a sec. Here's that orbit problem, right? I don't know if you could see that, but the idea is, notice the central mass is no longer fixed. You might be wondering, how would you handle this? It's not that outrageous. When we look in the code, notice this time, one of the masses, 8e10, is 8 times 10 to the 10, huge compared to 200. You could give it different momentum. Now keep in mind here, do you agree momentum and velocity are about the same thing? Does anybody remember the equation for momentum? P equals mv. Now, for physicsy reasons, which I don't really want to explain right now, physicists like to talk about things in terms of position and momentum instead of position and velocity in more advanced classes. So that's why I chose to do this. But basically, that's like telling you the velocity. Agreed? You just divide by the mass and you get the velocity. So this is effectively like the velocity. All right? Oops. As you go down into it, it's the same old junk, right? Gee, I wonder how I get, okay. Remember this one from before? That was the answer that we just found before, right? For the circular orbit, we could run this. Notice now the orbit is circular, right? Oh, but it's spiraling, so it's a helix. But notice the size of the circular orbit is not changing as this goes through space. You could use that problem that we did just before the break tomorrow in lab to figure out the special velocity or momentum you need for a circular orbit. All right. And then how do you do it this right here, right? You do a loop. You update the momentum, or sorry, update the position, you update the force, and then you do all this same procedure. We'll talk about this more in lab tomorrow. All right. Okay, so that's good for that. I hope that gives you a little foreshadowing of what we're doing in lab tomorrow. It's not terrible compared to some of the ones like center mass. Hopefully it'll be more fun. Plus you get to make stuff move. You can learn a lot. More of that. Here's the other thing. There's not a lot of labs you can do with, where am I on the screen? Which screen am I on? Oh. All right. Right. Think about this. How are you going to do a lab when your forces are 10 to the minus 11, right? We can't do that. So coding it is like one of the few ways you can actually get a feeling for this particular topic. This was actually the first topic that I did for a coding lab because I feel it really lends itself. Let me get these screens up. Do one more problem, call it a day. Okay, so we're going to look at problem 13.5 on page 119. Right? Last problem. Just sketch it out. I use green for 1 and red for 2. Horrible choice. Did I say green for 1? Okay. We have 3-point masses, and now finally we have to deal with some angles. Let's just start and put a star next to this one. You want to be expert at this, okay? I'm going to assume this is the y-axis and this is the x-axis just for no good reason, okay? And I believe we know mass 1 is 1.00 kilograms. Mass 2, 2.00 kilograms. Mass 3 is 3. We're keeping it simple. You can imagine I do complicated like 10 to the or something on a test. And then we're told this distance right here is 40 centimeters. And we're told that this distance right here, between these two, is 30 centimeters. Okay? So stay sharp for this one. Anything else we know? So we're looking at a top view. These are basically like 3 different balls sitting on a table. Got it. We know the center. Oh, those are center to center distances, right? Okay, got it. All right. If you had to guess, which mass is going to exert more force on object 3? Object 1 or 2? Again, will object 1 exert more force on 3 than 2? Or do you think object 2 will exert more force on 3 than 1? The green or the blue one? Which one's gonna push or pull harder on this thing? Sorry, I'm tired. What do you think? What's your gut tell you? Why do you say 2? What's your thought process?
More heavier.
Twice as heavy, right? Twice as much mass. That should increase the force. Is there anything that might counterbalance that or offset it?
More distance.
More distance. In the equations, which one matters more? Mass or distance? And what? Why? Distance. Why?
Because of the bottom of the equation.
And when it's in the bottom of the equation, when we're talking about force, it is squared. So you have a little bit more distance squared, but you have a lot more mass. So I'm not sure. I don't know. I don't care. But do you agree they're probably maybe in the same ballpark? You have more mass, but more distance. So let's assume for right now they're the same, and then let's find out which is bigger. I have no idea. What direction is the force on 3 from object 2? What direction is the force on 3 due to object 2? Show me with your finger. Okay. This is the force of 2 on 3, and I draw it on 3 because it's on 3. What direction is the force 1 on 3? Straight up. Probably about the same size. I don't know. Not to scale. It's on 3, so I draw it on 3. I know that seems stupid, but I really want you to have that on lock. Okay, now, if I want the net force on 3, please, please, please listen right frickin' now. The force net on 3, it's not equal to these two added up. You would think so. What I have just written is false. Why? This is not correct. Why? Rhymes with Hector. These are vectors. This is correct. This is correct. If you try to add the magnitudes, you get it wrong every time. I probably wouldn't be saying this unless this is probably on your final exam, because people screw it up every year and it makes me want to strangle them. So do not screw this up. You may not like it, but it's a vector. You have to add these as vectors, period. So in the previous problem, we didn't have to do that because everything was in a straight line. Do you remember that? Now we have I hats and J hats. Okay, enough said. Well, now we need to do our full vector force equations. Now I'm going to show you two styles of doing this, all right? So we're going to work this the rest of the day. Force 1 on 3 is actually the easiest way to do this one is to do magnitude in the positive j hat. Do you agree? We know it's in the positive j hat by looking at it. The other one isn't so simple, but this one should be what is the magnitude of it? What's the equation for the magnitude of this? What was the equation for the magnitude of gravitational force? G and 1 and 3, because we're dealing with 1, 3 now. See, we don't want 1, 2. Okay, so now you know why I was being so insane about these subscripts. When you start to have more than one mass, or more than two masses, excuse me, the subscripts start to be immensely useful. Divided by what? Which are?
3, 1.
Yep. And I'm just, do you agree that 1, 3 and 3, 1 would be the same because it's a distance? So then what? Squared in the positive j hat. Okay. help me out. What is R13 in this problem? What does that mean? What does R13 mean? Distance from 1 to 3. What is that? 40 what? What's that? Yes, you got it. We have to convert. Why? G, right? G is in units of meters. So the other mistake students make is instead of doing vectors, they also forget to get these in the right units. Right? Or they'll convert the units wrong. Okay. Do you agree at this point that's just a number you can punch it in and get it? This is the harder one. Now, this is kind of a, I need to move this label a little bit. So I'm going to move it to the end here. Force of 2 on 3. Do you agree we probably need some kind of angle here? This would be force 2, 3 in the X. Force 2, 3 in the Y. If we could just get this angle here, which maybe for no good reason I'll call theta, we could call it alpha, beta, whatever. Crap, I need that angle theta. Anybody know it? What's that? Something you're thinking about tangent, right? Tangent of what? Oh, that's true. Except we don't know these numbers yet. No, we need the angle to find it. So I need the angle from something else. That was a good thought. You're absolutely right. If I knew these two, I could take tangent and get it, or inverse tangent to get it, right? Is there a triangle here? Do I know this side in distance? Do I know this side? Isn't that 30? Isn't that 40? My eta theta. Now check this out. You could get the angle using tan inverse of 40 over 30. Agreed? Don't. Let's do it this way. What's sine of theta and what's cosine of theta? Just trust me for a minute. Or if you like that, do it that way, pass this class and go away. That's fine too. You want to just get the angle using tan inverse, move it down here, that's great. But just help me. If this is 30 and this is 40, what's this side of the triangle? 50. You could say, wait, didn't Jorstad tell us this is 53.1 degrees earlier in the semester and this is 36.9 and to memorize it? Yeah, I did. But why don't we just do SOHCAHTOA? What's sine of theta? Give me a number. 40 over 50? 0.8. What's cosine of theta? $30, which is 0.6. Why physicists love 3, 4, 5 right triangles, because sine and cosine turn out to be nice, easy numbers. Don't have a lot of weird decimals. That's why almost every problem from every class everywhere. Okay. All right. Well, let's do this over here. Force 2, 3 vector should equal force 2, 3 magnitude times cosine theta in the I hat plus sine theta in the j hat. Is that right? Something's wrong there. What did I screw up? It's close. It's in the negative I hat. Do you see it? This would be almost correct, but it's cosine theta in the negative I hat for this problem, to the left. You know what I'm saying? Is this reminding you of chapter 3? A little? What's F23 magnitude? What's the equation for it? Yes, big G, that one. You got it. Which masses do I use? 2 and 3. So once you get to harder problems, the subscripts are actually nice. What's the distance I use? R 2, 3 squared or not squared? Squared. And what is R23 in the picture? Half a meter. We were going to convert that so we could say 50 centimeters, but that'll screw it up. So we better use 0.500 meters. We know cosine theta is 0.6. You know sine theta, 0.800. I'm going to pause and make sure you guys agree with that. It might not be exactly the same as the way we already did it, but it's nearly identical. So I want to give you a second just in case. Does that make sense? In particular, I guess, right? Hopefully you agree. We can get the magnitude. We could do SOHCAHTOA. And here I did SOHCAHTOA kind of in this weird way where I looked at this picture. And I said there's a minus cosine for this side, right? I think before what we always did was we'd say it was force 23 cosine in the negative I hat plus force 23 sine theta in the positive, right? Remember we did that before? All I did was I just wrote the magnitude and split out the cosine and sine. Good? Yeah, thumbs up, thumbs down. Just let me know. Okay. Check this out. This is great. It works for any planar objects. On your final exam, I'm not going to do 3D. So this would work on your final exam. If you feel comfortable with that, great. However, because we're coding tomorrow in lab, and because it's more general, I want to show you a different style of doing this. It is also G M2 M3 over radius 2, 3 cubed times radius 2, 3 vector negative. Remember that? So instead of saying r squared times r hat negative, we could do this. Somebody give me the vector for r 2, 3. I want to go. Remind me, is R23 from 2 to 3 or is it from 3 to 2? What is R23? 2 to 3. We're going from 2 to 3. Somebody tell me how much you have to move in the I hat and J hat. Give me R2 to 3 in Cartesian form. How much in the I hat? 30. Positive or negative? Right, I'm going positive in the I hat, and how much in the J hat? So that is going to be give me a second. How about I say it like this? Now, at first, this looks very different. But when you plug it in, this ever crucial minus sign, it's so crucial that you get the minus signs right. When I stick that in, notice the I hat becomes negative, the J hat becomes positive, I get the correct direction. So the math works out. This method is better in 3D and in code. That's all I wanted to tell you. Oh, crap. Why is this going to give me trouble when I punch it in? The units, right? We got to remember, we got to always use meters. So that's bad. Let's rewrite this in terms of meters. That would be how many meters here? 0.300. And this would be right? We've got to always watch those units. So when you're doing this on a test, watch your units, watch your minus signs. Remember that these are vectors. You have to add the forces as vectors to get the net force. If I ask you for the magnitude of the net force, how would you get the magnitude of the net force? Let me do this real quick. Let's say I punch in the numbers. You guys can do it real quick. I'm going to cheat and use the solutions real quick. I'm just going to get the numbers for these, okay? You can check it, see if you can beat me while I'm searching. See if you're faster than the internet. You might be at this point. This is chapter 13, number 5. I did this both ways in the solution, so you could try and do this again at home. And it looks like I got a bunch of numbers, and when we plug it in, I'm going to write this on the other page. I'll switch the camera over in a second. Yeah, just give me a second. You guys keep working. What was it? Nanonewtons. Weird. I will switch it over, I promise. It's in the solutions if you're not wanting to wait. Just give me a second. Crap. I got to punch in some numbers too. 0.6. 0.6. 0.96. I can be sloppy with 6 figs. 28, is that right? I'm going to switch it over. So if you do a lot of this math and plug it in, just in the interest of time, so you can go home. It did again, full solutions later. Oh my gosh. Come on. There. Okay. Got a bunch of numbers. I got nanonewtons for these, okay? So you get the force vector from number 1, the force vector, and now you got to add the i's with the i's, the j's with the j's. So out of all this, whoa. I'll keep it as a vector. We get negative 0.96 in the I hat. Plus, what is this? 253. By the way, if you're curious, this one ended up being 1.6 nanonewtons. It was slightly larger. You were right, the blue one. Remember that? Yeah, they're way back earlier. Turns out they're pretty close in size, but the blue one had twice the mass and the radius was about the same. Right? We only had 25% more radius, so it turns out the blue one was bigger. How do I get the magnitude? How would you get that? Remind me. Yes. Oh, shoot. What did I forget here? Why did I screw up? What did I forget? Units. If you want to do that, what I would recommend is draw a quick picture. About 1 this way, 1, 2.5 that way. Does that look about right? This side's 0.96 to the left. This one's 2.53 up. Marco, what were you saying earlier? How could I get this angle phi? You got it. So Marco said it, phi was equal to tan inverse of what over what? Yep. And then you can think about minus signs and whether or not you want to use it. Ryan, what were you saying here? This side is?
It's 0.96 squared plus 2.53 squared, all squared.
And so you can get the magnitude and the direction. The classic thing that I might do in a test is ask you for the magnitude. Everybody's tired and they just add the magnitudes and I want to strangle them, but that's not what you're going to do. I'm going to ask you for the magnitude and then you're going to add up the vectors and then do this process at the end, right? Or I'll just light your paper on fire and cry, okay? Or dream about doing that. I don't know. It's like a physics teacher's worst nightmare. They keep adding magnitudes together. This is a vector. We've been doing this the entire semester. You got to get it right once, please. I swear you can do it. Check this out. Couldn't we have eyeballed this a little bit? Take a look. I'm gonna cheat and do the parallelogram rule. Graphical tail to tip, tail to tip. There's the net force. It's somewhere in between there. Does this look a lot like that last vector we drew? Tall and skinny? Yeah. So the purpose of trying to think about this and draw it well at the beginning is just to give you a feeling. We expect it should be in the third quadrant, or what's the, it should be in the second quadrant, my bad, 1, 2, and it should be close to the vertical axis. Okay, by the way, on an axis is not in a quadrant. I looked it up too. Okay, anyways, not that I'm, you know what I'm talking about. Let's leave it at that. It's time to go.